Hello, welcome to the session. In this session, we will discuss about how the model of Maruti Swift Dzire that we already built performed when it is powered by 50 HP 240 volt DC motor. So now hope you completed your task and derived the characteristic from the Maruti Swift Dzire and stored in the lookup table. This characteristic is stored in this lookup table. This is speed torque characteristic of Maruti Swift Dzire model that we have built. And this is the 50 HP 240 volt DC shunt motor. So I already shared the data sheet. You will have all the data. I already filled the parameters, right? So we cannot select the model from this preset model because we want to change the total inertia according to its mass. So its mass is 1335. So 1335 kg. So I just change it, and all other parameters I already fill it: resistance, inductance, mutual inductance, right, and friction component. So now supply voltage is 240 volt according to its rating, and the field voltage is 300 volt and rated speed is 1750 rpm. So first we will see the performance without having the current limiter and any speed control, and then we will add the current limiter. So we will see how it works. So you can see current goes extremely high and then it is reducing. Speed is 187 km/h. I am just stopping the simulation and observing the speed response in terms of performance. You can see performances look very good because in the fraction of second we are achieving the hundreds of km/h speed, but here we can not do it because initial current is too much high and we are not allowing it. It's more than 1800 ampere. So this current is too much high and reducing to its normal value. So first we need to find the rated current. We must limit the current to the rated current, and we can also use the speed control system with the current control. So here we require the current limiter, and then we can see the actual performance, because this is not actual performance. This is not gonna happen in any motor. So all motor will require the initial current control to protect the winding. So we will just add the current control loop that we already discussed with the help of voltage control source instead of this DC source. So here is the closed loop system with the current control as we already discussed, but before that first we need to calculate the rated current. So for calculating the rated current we require the efficiency. We are assuming the very good efficiency of around 85% and calculating the input power. So when we assume the efficiency is 85%, that means 0.85. it is equal to output power divided by input power. So 50 HP equivalent to 37.285 kilowatt. So we are having output power. So output divided by input is efficiency. So we can calculate the input power is equal to output power 37.285 divided by 0.85. It will give the figure input power in kilowatt 43.86 kilowatt. So now we are having the input R and input voltage 240 volt. So input power 43.86 kilowatt divided by the 240 volt will give the value of rated current in ampere, 182.7 ampere. So input power is 43.86 kilowatt and rated current is 182.7 ampere. So we will restrict the current to rated current and plus or minus 2. Here it is 182. Okay, and here I am using the plus 2 and minus 2 ampere switching to restrict the current limit, right? So it will restrict the initial current as well as we can control the speed from here. We can also calculate the rated torque. So to calculate the rated torque we require the speed in radian per second. So 1 revolution is 2 pi radian. So 1750 multiplied by 2 pi will be radian per minute, and 1 minute is equal to 60 seconds. So divide by 60 will give us the radian per second. So 2 pi divided by 60, that means multiply by 2 and divide by 30 will give us the speed in radian per second. So output power is equal to torque into speed, torque in Newton meter and speed in radian per second. If we have the speed in radian per second, we are having power, the torque is equal to power divided by the speed. So it will give the Newton meter torque. 203.55 Newton meter is the rated torque. So we can also see what is the amount of torque is applying and opposing the motor at any time. So let's observe the performance. You can see current is restricted. We are interested in observing the initial current, so we get the idea what will be the acceleration, how much second it will require to reach the speed of certain 60 km per hour or the say 100. So we are running it, it's almost 70 seconds is completed. So speed is increasing. You can see to have the maximum speed we need to wait for the simulation. Almost 100 second simulation is completed and speed is still increasing because our current is still not reached rated current. Motor is working on the rated current. So even after the 200 second, let's see, speed is increasing slightly. See here. So what is happening? See this response. Now for the 0 to 60 it required the, let's expand this area so we can have exact idea. So it requires almost more than 20 seconds to reach the speed of 60 km per hour, 34 seconds exactly. So time response is slow because we require to limit the initial current. So when we use the DC shunt motor, we are not getting the high starting torque and high acceleration as we get in case of DC series motor or the BLDC or SRM. So this is the issue with DC series motor, and this motor is also not purposefully built for the EV application, but it has the 240 volt and 182 is rated current. So here you can see current is reducing in the rated current and we are reaching the speed more than 180 km per hour speed is achieved, but only the issue is of starting response. So acceleration is slow, otherwise you can use it. So in case of application like the train for the long distance or the goods carriage, so it is okay, but DC shunt motor, that's why is not recommended for the power bike and the car. So but by this way we can analyze any vehicle model, how one motor will perform in case on the any vehicle model. So this method gives us flexibility that we can have the two separate model. We can have the one model for the vehicle and one model for the motor, and we can predict the performance of how the motor will perform on particular vehicle. We can also control the speed on runtime by varying the current from here. You can see for this speed also current is very less than the rated current, so motor is still can inject the higher current when it is demanded by the load, so it can reserve for the slope, so it can also achieve such speed in case of slope by increasing the current. So this all can be analyzed and conducted.